carrying forward from our last lecture. Let me just present my screen. Yeah, can you all see the screen now?
Yes, sir, it's visible.
Okay, all right. So, if you remember our last lecture where we just initiated our discussion on what exactly econometrics is all about, and why it is and how it is different from other quantitative techniques that are used in economics, where statistical methods are concerned, mathematical methods are concerned, and then we finally understood that econometrics is a study or is a branch of economics which deals with analysis of economic data using mathematical and statistical concepts with the purpose of giving empirical content to economic theory. तो सबसे जो इम्पोर्टेंट चीज है इकोनोमेट्रिक्स स्टार्ट करने से पहले is that you must have a precise theory about the variables under question, because the theory will completely specify a set of precise and deterministic relationships among variables, because ultimately we are concerned with finding out the causal relationships amongst variables that flow from one variable to another. In particular, as far as econometrics jargon is concerned, we have, one set of variables are called as dependent variable or explained variable, or they are also called as regressions, and they are usually denoted by y. And on the other side, you have the other set of variables which are called as independent variables. Then you have regressors, or they are also called as explanatory variables. I'm just writing in short notation. They're usually denoted by x. So ideally क्या है? मुझे दो variable पता है. It may consist of more than one variables as independent variables, and I finally want to understand the causal relationship that flows from x to y. There are many situations in economics where you also have a bidirectional causality. By that I mean that x influences y and in turn y also influences x. For the time being, we are not talking about simultaneous equations here, but we'll definitely study simultaneous equation. So as far as, estimating a causal relationship from one variable to another is concerned, one of the earliest model, or you can say that the linear regression model is a single most useful tool that is available at the hands of econometricians. अब ideal क्या है? There will be a theory, there will be an economic theory which will define a precise and deterministic relation between y and x. Now, what kind of function will be there that will exactly be defined by the literature? How many variables to be included in the model? That again depends on the research carried out by the researcher. So the number of variables, x's, in the model, what kind of functional form between y and x in the model gets decided by the researcher himself or herself. But where exactly an econometric model differs from that of a mathematical model is that an econometric model is stochastic in nature. Stochastic means that no matter how accurate your estimations are, how accurate your best guess about any measurement of economic variables are, there is bound to be an error. And it is precisely this error term, they are also sometimes called as disturbances term or random disturbances term. They are precisely called as disturbances because they otherwise disturb and a stable relationship between y and x. So, we had mentioned about this, that the way we write an equation or an econometric model in linear notation is that we write that y is some function of x1 to xk if there are k number of explanatory variables and plus a random stochastic term denoted by u. So agar ye u nahi hota, then it would definitely be a deterministic relationship between y and x. By assigning an appropriate functional form, by this function I mean to say that y can be a function of log of x, y can be a function of x square, y can be a function of x cube, y can be a function of sine of x, and so on
Size
and
of the
so forth. You can
question,
find a
whether it's
plethora of
basic
functions
questions
like
or
this.
advanced
Y can
questions, don't
also be a
worry.
function of
You have to
ex.
ask me the
And in
questions.
all these examples that we've
And then
taken,
if
we are
everything
talking
is
about
clear, then we go ahead.
transformation of these
Yes,
x
sir.
variables. But you can
Sir, we are
simply also have transformation of y variables as well.
Find out what is the
So
latest. They
this
have already
functional
heard a particular
relationship
zone.
or this functional form determines the exact form of relationship that exists among the variables y and x. Here y is a function of x square. Here's y is a function of x cube. Here y is a function of exponent of x. Here y is a function of sine of x. You can simply have y as a reciprocal of x. Y is a function of reciprocal of x. And so on and so forth. You can find on, go on finding the variables. So that's why they are called as econometric model, because this error term, this disturbances term, disturbs an otherwise stable relationship between y and x. Now, so y is called your dependent variable, these x's are called your independent variable, and this u is called your random disturbance term. Now, how exactly we write an econometric model as far as linear regression model is concerned, and if I recollect properly, then we just defined what linearity as a term refers to us. Is that the linear stand for the linear relationship amongst variables? The answer is clearly no. By linearity, we mean to talk about how parameters, which we'll talk as our lectures go on, the parameters which enter as coefficients for these k number of explanative variables and the error terms. So the way these parameters and error terms enter the equation, if they enter linearly, such models are called as linear regression model. So, I can write y as a function of, beta 1 x1 plus beta 2 x2 plus beta 3 x3 से लेके beta के xk plus a random term u. Now, when you write an equation in this form, they are called as population regression function or population regression equation. And the idea why they're called as population regression equation is because somehow this model or this linear model, why linear? Because the way parameters beta 1, beta 2 से लेके beta k and this u enters the model. And since they enter linearly, that's what they're called as linear regression model. So ideally, बहुत सारे books में या बहुत सारे interpretation ऐसे भी होते हैं that this linear regression model itself is an approximation of the relationship that exists amongst these variables. So at best, how y along with these k number of explanative variables are scattered or are distributed across a population, this linear regression model is itself said to be an approximate or an estimate of the actual relation that exists amongst these variables. And they are called population regression function because they are exact estimate about how in population, if I'm talking about this universe as the set of population, how in this population these variables behave or move with each other. So this is called as population regression equation of y on these x's, y on x1, x2 से लेके xk, plus a random error term denoted by mu, or in some notation they are also denoted by epsilon. However, we'll reserve epsilon term for sample error terms. Because you understand that ultimately, if this is a population regression function, which we assume that this is the way the relation between y and x's can be estimated from the population. And since population, you must understand that precisely both these terms are unknown. unless you have the values of beta 1, beta 2, beta 3, select beta k, which itself is the best guess about these parameters. You do not exactly know this deterministic component as well, and this along this error term, we do not know anything about how the error terms in our equation behaves, and that's why all the assumptions are there for the error terms. So this mu is called as random disturbance because we just understood that it disturbs a stable relationship, and these disturbances can arise for several reasons. Primarily because we cannot hope to capture every influence on an economic variable in a model, no matter how elaborate your model is. The net effect of these random disturbances, which can be positive or negative, of all the omitted factors that I have not explicitly included in the deterministic part of the model, they are commonly referred to as random disturbances. However, there are other contributors as well, and probably one of the most significant contributor to this error term is they are called as errors of measurement. Because no matter how accurate your measurement scale is, there is bound to be errors, and such errors are one of the single most significant contributor to the random disturbances term of the population regression function. So ideally क्या है, how should we visualize this entire process? Entire process ये कहता है that each observation in a sample, so suppose that I have the dependent variable y and I have independent variable denoted by x1 till xk. So what is population regression function all about, and why we assume this to be linear, what exactly this represent to us, or what exactly this conveys to us. So with regard to that, how do we visualize this notation as that if these are the k plus 1 variables that we have, depending on the researcher, so we have k number of explanative variables and y is the single dependent variable as far as the model is concerned, and if you collect observations on these k plus 1 variables, so let me write this as yi, which tells you that I is the subscript denoted for the observation. And let us say you collected a sample consisting of n number of observations. So sample consisting of n number of observation means there is a single sample, the size of that sample is n. Now size of the sample means this sample consists of n number of observations on these variables denoted by y, x1 and till xk. So I can write, or I can understand this whole population regression function as that each observation in this sample, let me write it as xi1, xi2, select xik, which tells you that if I'm talking about I is equal to 1, that is first observation, so y1, x11, x12, select x1k, that is first observation on the explanative variable 1, first observation on the explanative variable 2, so on till first observation on explanative variable k. Similarly, if I'm talking about I is equal to 2, this can be written as y2, x21, x22, select x2k. What it tells you is second observation on explanative variable 1, second observation on explanative variable 2, so on till second observation on explanatory variable k. And if you go on repeating this for n number of observation, I can think of this population regression function to be denoted by I beta 1 xi1 plus beta 2 xi2, so on beta k xik plus mu I. And now I'm sure that you are smart enough to understand that this yi is a column vector consisting of n number of observations on the dependent variable y, so I can write this as n times 1. So this yi is a column vector consisting of n number of observations on this dependent variable y. Similarly, this xi1 is the column vector consisting of n number of observations on the explanatory variable 1. This xi2 consists of n number of observations on the explanatory variable 2. So on, this xik should be understood as n number of observations on the explanatory variable given by xk. And mu I is the random vector, or is a vector consisting of random disturbances for each of the observation. So this is also a column vector where you have n number of disturbances for each observation. So I can write this as n times 1. Now, here you see, if I think of this as x11, x21, x31, select xn1, similarly x12, x22, so on till xn2, x1k, x2k, so on till xnk. And if I assemble this entire variable or entire values on the variable x, so this can be thought of as a matrix consisting of these column vectors, where these column vectors represent n number of observations on each of these explanatory variables. And the dimension of this matrix will be n times k, where n denote the number of observations and k denote the number of explanatory variables. So n denotes the number of rows. So in total I have n number of rows in this matrix, and k denotes the number of columns. So I have 1, 2, select k number of explanatory variables. So the dimension of this matrix is n times k. Now look at this equation, how this equation actually pans out. What I notice is that this data matrix, which is also called as data matrix, because this is the matrix which contains information on your independent variables. And why are they called independent variables? Because the autonomous variation in such variables can be thought of outside the model. However, any variation in this y has to come from variation by these variables, and that's why this is called dependent and this is called independent variables. Now you see, what is happening, that this beta 1, which is a coefficient given for x1, beta 2, a coefficient given for x2, similarly beta k, a coefficient given for xk. So if you manipulate this little bit, you can think of this as that beta 1 gets multiplied by x11, x21, so on till xn1. Similarly, beta 2 gets multiplied by x12, x22, so on till xn2. And by the same analogy, I can think of that this beta k is multiplied by x1k, xnk. And what I'm doing after that, I'm simply adding them up. So exactly what it tells you is, that each of these column vectors get pre-multiplied by a coefficient variable given by beta 1. They are also called as parametric constant. And since these parameters enter linearly in the model, this deterministic component can be understood as linear combination of x's. So y can be thought of as exactly composition of two parts, where this first part is called as linear combination of x's, or the deterministic component or non-stochastic component, and this u is called as column vector consisting of n number of observations for each of those residuals. So this brings an element of stochasticity. So this is called as stochastic component. Now you see, the way I have written the model, it must mean that the model is called linear because first these parameters enter linearly in the model, that's why it's a linear combination. Also, this error term or this disturbances term, it is also additive in nature. And that's why you're able to write them as separately as part of two components. Once we go ahead in the course, we'll understand that they are also orthogonal to each other. And that's why we are able to add them like this, because ultimately they are nothing but an addition of vectors. And if you are able to add vectors like, without having any angle between them, it must mean that they must be orthogonal to each other. There must be an angle of 90 degrees between them. That's why you are able to simply add them like you do for normal addition, which we'll discuss once we go ahead. But this whole population regression function can, in shorthand notation, if I write them in vector notation, I can think of writing them like this, where this X is your data matrix consisting of n by k as dimension, beta is your coefficient vector, iska dimension over k by 1, k number of explanatory variables in one column. That's why the matrix multiplication is conformable. So n by k multiplied by k by 1. So this will be your n by 1 dimension. And this is mu, which tells you, or which gives you the column vector consisting of n number of observations on the residuals. And here you have column vector consisting of n number of observations on the dependent variable. So in shorthand notation, in vector notation, in matrix notation, your population regression equation, why I'm saying the population regression function, because I'm still using the term beta. And these betas are nothing but the population parameters. Because this is how you assume that each observation in the sample is generated by an underlying data generating process, where it is assumed that the data generating process follows this model or follows a linear model. So the first assumption of linearity in matrix notation can be understood or can be written in this form, where the assumption of linearity, the model specifies a linear relationship between y and x1 till xk, where this linear relationship is given by the way parameters and the disturbance system enter in the model. Now, what exactly I mean? So, what do I mean by when I say that the way parameters and disturbance system enter the model linearly is that even if your model does not appear linear in the first place, if somehow, if through some suitable transformation, you are able to make the model linear the way we have defined them to be linear, as long as you can carry on those transformations, you are good to go. You are good to go for estimation of such model using classical linear regression techniques. So what do I mean by saying this? That suppose your population regression function is given by this equation. Now, in first glance, this appears to me as a non-linear model because beta does not enter linearly over here. But if you see, if I take logarithm both the sides, if I take natural log both the sides, so it will be ln y, ln a plus beta times ln x, plus mu. And if I just replace this ln a by, let's say, a star, this ln x by x star, so I can write this beta x star plus mu, and it is and ln y by y star. Now, through this logarithmic transformation of these variables, I am able to convert this otherwise non-linear model in parameters to a linear model in the parameters and the disturbance system. Now look at, since in this original model, in this original population regression function, this error term enters exponentially and multiplicatively. That's why when we took natural log both the sides, this enters additively in the transformed model. Whereas if the same equation, the population regression function would have been written like this, there is no transformation whatsoever which makes this non-linear model being estimated by linear regression model. And this is precisely what I mean when I say that it is not just these parameters, the way they enter the model linearly, it is also that the error terms or the disturbances term enter the equation in an additive fashion. So this is the first assumption, and this is one of the very important assumption because somehow it gives a precise functional or precise mathematical form to the linear regression model. Now, many times we are confused that exactly what these assumptions are for. So, just listen to this point very carefully because they're very seldom mentioned in any of the standard textbooks that we read. Ultimately, these assumptions, or let me put it other words, these classical linear regression model, it consists a set of assumptions about how a data set will be produced by an underlying data generating process. So ultimately these assumptions are for the way data gets generated for the model. So whatever assumption that we have, this is the assumption about how a data an underlying data generating process, which we assume it to be like linear in this nature, how a data set will be produced by this underlying data generating process, where what kind of functional form, that is what kind of that f will be taken, will get decided by the relationship or the theory which determines a relationship between dependent and independent variable. And then these assumptions, these describe the form of the model and relationships amongst its various constituents. So again, I repeat this point. The assumptions of CLRM is about how a data set will be produced by an underlying data generating process. So to begin with, we assume that this Y is a linear combination of all the x's that we have explicitly included in the model. This is an assumption. And this is an assumption about how y and x are related. So if it was not for any random error disturbances term, then we had discussed in our last lecture as well that linear combination of vectors precisely lie in the space spanned by those vectors themselves. That is, if y is supposed to be a linear combination of x1, x2, and if y is definitely, let's say y, I can write ax1 plus bx2. This is what linear combination is all about. You take the vector x1, you take the vector x2, you multiply that vector by a scalar quantity a, you multiply x2 by b, and you simply add them. So this y has to lie in the space spanned by these two vectors x1 and x2, and that's why we say that it's a deterministic relationship. But precisely this y, since this y does not lie in the linear combination spanned by the x1 and x2, this lies outside the model. So if I'm assuming that this is my x1, this is my x2, and somehow let us assume that this is the y. So this y lies inside or in the space spanned by x1 and x2. If this is the case, then y exactly is written as a combination of some function of x1 and x2, and there is no need of econometrics at all. But precisely this y lies outside the plane or outside the space spanned by these x1 and x2, and the distance of this estimated value from this actual value is called your error term. I'll talk about this geometric interpretation in detail, but this is how you should visualize this.
Sir, can you repeat this part when we take y outside?
Yeah, see, this y lies outside of the space. So suppose ये आपका मान लीजिए एक टेबल है और इस टेबल के ऊपर suppose you understand that this point lies outside the table. So what I'm saying that suppose if this is x1 and this is x2 vector inside the table, and if this is y, which is a linear combination of x1 and x2. So in order to reach to this point, in order to reach to the actual y which lies outside the table, I reach exactly to that point which lies exactly below the actual value of y, which is what is called as estimated value of y. And the difference or the distance between, let me say that this point I am denoting by this vector. So ये जो vector है, ये y vector, this lies in the plane or in this table, on this table, and y actually lies outside the table. So किसी भी दो point के बीच में जो minimum distance है, that minimum distance is the perpendicular distance, and I want to reach exactly at that point on the surface which takes me exactly below the actual value. So the distance between the actual value and the estimated value on this basis of x, let me write it like this. This is your error term or residuals. And precisely there exists an angle of 90 degree. One second, guys.
So I don't understand the reason why we're still taking it inside.
क्या? हाँ सर. नहीं सर, मैंने चेक किया है, उसमें आई डोंट थिंक है बच्चे सारे प्रेजेंट. हाँ हाँ, वो क्योंकि सर अपडेट वो दूसरा शीट अपडेट होके चला गया था, मतलब किसी और का मार्क्स था वो उसमें चला गया था, इसलिए उसमें सारे बच्चे का प्रेजेंट आ रहा था. अभी मैंने रिवाइज करके आपको भेजा है और उन्हीं बच्चों का जिनका मेल पे एक्चुअली उन्होंने आंसर सबमिट किया है. आई थिंक सर मार्कशीट नहीं मेरे पास, इसलिए थोड़ा कंफ्यूजन हो गया है. एक बार आप मार्कशीट भेजिए, उससे फिर मैं चेक कर लूंगा कि अभी मेरे पास जितना मेल था उसमें मैंने फिर माइक्रो के मार्क्स रिवाइज किया है फाइनेंस वालों का, बिकॉज आईबीएफ का तो सही था. अच्छा ठीक है, तो एक बार क्या सर, जो आपके पास है मार्कशीट वो प्रेजेंट एब्सेंट वाला शीट होगा ना, आप मुझे एक बार मेल कर दीजिए, तो फिर से मैं चेक करके आपको देख लेता हूँ, क्योंकि हो सकता है मैं मेल स्किप कर गया हूँ, बट जितने बच्चों को मुझे दिखा अपने मेल पे उसको है मार्क. ठीक है. हाँ सर. Sorry. Yeah. Someone was asking. Yeah, go on.
Sir, am I audible?
Yeah.
Yes, sir. So I was asking the reason why we are still taking it inside.
Why we are?
Still taking it inside the box.
Why we are, come again, what we are doing inside?
Why we are still taking it inside the box?
Because precisely y is a linear combination of x1 and x2, no? Linear combination means, हमने उस दिन ये plane जो आपका जो, one second. ये जो quadrants बनाते हैं सिंपल 2 डायमेंशन का, ये आपका x dash, ये y dash, ये exactly these quadrants are, what are these quadrants? If you imagine this to be a surface of a table, and if you take a unit vector in the direction of x, call it I hat. If you take a unit vector in the direction of j hat, and by any suitable linear combination of I hat and j hat, precisely because they are linearly independent vectors, so a I hat plus b j hat combinedly explains all the points on this quadrant. It can be minus 3 I hat plus 4 j hat. It means you are talking about minus 3 and 4 it means I'm talking a vector which takes me here by combination of I hat and j hat. If I'm talking about, let's say, 2I hat plus 4j hat, it means I'm taking 2 in the x direction, 4 in the y direction. So somewhere this is the vector. और इस तरह करके all the vectors, if I'm able to write them as linear combination of these unit vectors, they will also lie in the same space. So if I'm writing y is a linear combination of beta 1 x1 plus beta 2 x2, it means that part of y, which is a linear combination of vector x1 and x2, will lie in the plane spanned by these two vectors, x1 and x2. But actually, since this y does not lie in the linear combination, that's why I'm plotting this y outside the space or outside the plane spanned by these two vectors. And since this vector, which is a linear combination of x1 and x2, it will lie inside the plane spanned by x1 and x2. And precisely because this is not the y which is my actual y lies outside the space or outside the space. So the difference or distance between the actual y and the estimated y, this is called your error. I talk about these geometric interpretation. But this is how it should be understood, that why I'm taking inside the table, because exactly this is what your linear combination of vectors mean. Am I clear?
Yes, sir.
Okay, all right. So let us move forward. And so first assumption जो था हमारा linearity का, अभी हम just discuss करते हैं कि assumption actually है किसके लिए. So ये assumption है कि आपका data set कैसे produce होगा. एक underlying आपने data generating process जो assume किया है. So उसका first assumption ये है that my regression model is linear in parameters and additive in disturbances. And if I'm writing, so assumption number 1 is your linearity. And in shorthand notation, in matrix notation, this can be written as x beta plus u, where you have to understand this is y is a column vector, this mu is a column vector, this x is a data matrix, and this beta itself is a column vector consisting of those coefficients. Okay, all right. So let us move forward and discuss the second assumption, which is a very interesting assumption, which is one of the most important assumptions as far as linear regression model is concerned. This assumption is called as assumption of full column rank. Now, what do you understand by rank of a matrix?
So maximum number of linearly independent rows or columns.
And what do you exactly mean by linearly independent rows or columns?
So one row or column is not basically we don't get by scalar multiplication the other row or column.
Correct. So linearly independent rows or columns refers to that none of the rows or columns can be represented as a linear combination of other rows or columns present in the matrix. So this assumption is about full column rank. Now if you actually see the data matrix, how a data matrix looks like, if I am taking n number of observations on each of those k number of explanatory variables, so n, that is rows, denote the number of observations, and this k denotes the columns, and columns here refers to the number of explanatory variables in the model. So if this is x1, first observation on 1, second observation on 1, so on till nth observation on 1. Similarly, first observation on variable 2, second observation on variable 2 से लेके nth observation on variable 2. So on, first observation on k, nth observation on k. So this assumption of full column rank means what? Column यहाँ पे क्या represent कर रहा है? Column represent कर रहा है explanatory variables को. Your x's. Full column rank means what? Full column rank means all the columns are linearly independent of each other. That is, column 1 should not be if this matrix consists of full column rank, then column 1 should not be represented as a linear combination of any two columns or any of the columns present in the matrix. अब इसका लॉजिकल रीजनिंग क्या है? Let us understand that. अभी हमने क्या बोला that once I write my population regression model like this, so all the explanatory variables which are explicitly included in the model and all other variables which might or might not have affected or impacted this dependent variable, they all are included in the error term. तो अगर आपने let's say आपने 3 number of explanatory variables explicitly include किया अपने मॉडल में, and out of those 3 number of independent variables, let us say one of the independent variable or one of the explanatory variable can be written exactly as a linear combination of the other 2 independent variables. So let us say you took x1, x2, x3. Let us say this is your labor income, this is your let's say non-labor income, this is your total income. So what I notice is that some combination, so x3, that is total income, is let's say 0.7 times x1 plus 0.2 times x2. It means total income can be exactly represented as a linear combination of labor income and non-labor income. It means it was not needed for me as a researcher to include x3 explicitly in the model. Because this x3, whatever information it conveys, can exactly be conveyed by a linear combination of x1 and x2. It means if I have 3 number of explanatory variables in the model, and if my matrix does not have full column rank, it means one of the independent variable can be exactly written as a linear combination of other 2 variables in the model. This is sometimes also called as assumption of no perfect multicollinearity. Because if you remember our discussion on how a linear combination is defined, for a linear combination to be defined, the vectors must not be collinear with each other. That is, they must not lie on the same line. Because if they lie on the same line, there cannot be a linear combination obtained out of this vector, and which is precisely the assumption of full column rank is. So ये assumption क्या बोलता है? That there are no exact linear relationships among the variables. So assumption is that if X is a data matrix consisting of dimension n by k, then this X has a rank of k. Hence, X has full column rank, whereby it implies that the columns of X, all of them are linearly independent, and then this, a redundant assumption that at least n should be as large as k. That is, जितना number of your variables है, उतना observation तो at least आपके पास होना चाहिए, otherwise you will not be able to solve the system. So this assumption of full column rank means that all the columns of the data matrix are linearly independent, and there are at least k number of observations. This assumption, by the way, is also called as identification condition. Because if this assumption is not fulfilled, or if this assumption gets violated, assumption of no perfect multicollinearity. Again, understand this part. Why I'm saying that no perfect multicollinearity means is that I do not want the vectors to be exactly collinear with each other. There can be a very, very high degree of relationship, or very, strength the relationship between the variables or the vectors is very, is of full strength. But as long as it is not collinear or there are no exact relationship amongst the variables, till that point I am fine. And again, multicollinearity is an assumption which more or less is all about degree or degree of tolerance. If researcher is comfortable with having a very high correlation amongst the variables that is included in the model, as long as they are not perfectly collinear, multicollinearity is more of a problem of degree. What is that degree of collinearity? If that degree is sufficiently high, which becomes intolerable for the researcher, then you have a problem. You must do something about it. And if the model suffers from multicollinearity, then you must definitely do something about it. Otherwise, you will not be able to run your model. That's why this assumption of full column rank is also called as identification condition. और इसका एक बहुत ही सिंपल corollary है. और हाँ, एक और चीज, most of the time the CLRM or linear regression model that we understand, most of the time they are assumed to be or to include a constant term. By this, what I mean is that आपने देखा होगा, your model written as beta naught plus beta 1 x1 plus beta 2 x2 plus beta k xk plus u. Now this beta naught, which is there included, and it is called as intercept term, because running a linear regression model without a constant term poses infinite number of problems, which we'll deal once we discuss regression without a constant term. So how this is incorporated in the data matrix? If you remember, the way we had written all these x's, so if this is x11, x21, select xn1, n observation on the independent variable 1, x12, x22, select xn2, similarly x1k till xnk. How did we write this? We multiply this with beta 1, beta 2, beta k. And if this beta naught does not contain any x's, it means it must be a column consisting of 1. And then this gets multiplied by beta naught. So this is how generally your population regression functions are commonly reported like this. Because not having a constant term has certain implications which are very harmful. We'll discuss about them. For the time being, understand this beta naught consisting as an intercept term in the population regression function, where this beta naught is multiplied by a column vector consisting of ones. So let us say your population regression function is beta naught plus beta 1 x plus mu. And then you have n number of observations on y. So let us assume that this y is a column vector consisting of n number of observations. Then you have a data matrix. In order to incorporate for this data, for this intercept term, the first column of your data matrix consisting of n number of ones. Second column of your data matrix will consist of n number of observations on this single explanatory variable in the model. So it will be x1, x2, so on till xn. Now when you have only single explanatory variable in the model, what exactly does it mean to have full column rank? Full column rank means कि in this case I have two number of explanatory variables including the constant. Both the columns must be linearly independent of each other. And they are called as two variable linear model because there is only two variables involved, y and x. So the assumption of full column rank for a two-variable linear model with a constant term means that there must be variation in this regressive X. That is, the observations on the single explanatory variable that we have, there must be sufficient degree of variation amongst the observation in this regression X. Because if there is no variation in X, you understand that if let's say it is 2, 2, 2, 2, so what will happen is that this column will be exact twice of the column 1. So if there is no variation in X, then what it means that all our observations related to Y will lie on a vertical line. And this presumably should lead you to conclude that there is a flaw in the data set. And why there is a flaw in the data set? Because there is a possibility which suggests that you could have drawn a sample in which there was variation in X, but in this particular instance, you did not draw a sample having variation in the regressor. So the assumption of full column rank is about the assumption in common terminology is referred to as no perfect multicollinearity. That is, no two vectors must be entirely or perfectly collinear with each other. And when I refer to as the problem of degree, what it means is that ultimately it depends on the degree of correlation amongst the variables which researcher can tolerate. As long as these variables are not perfectly collinear, researcher is fine with this. So the assumption of full column rank, again a very important assumption, is also referred to as identification condition. Please remember this.
Sir?
Yeah.
Sir, could you please repeat that part, full column rank in a single variable?
Full column rank in single variable, come again, in a two variable thing?
Yes sir, sorry.
So yeah, so full column rank means क्या हुआ कि आपका जो दोनों कॉलम है वो आपस में linearly independent होने चाहिए. और अगर आपके पास टू वेरिएबल मॉडल है जिसमें आपका एक कॉलम जो कि इंटरसेप्ट टर्म के लिए है, which is there just to incorporate the column consisting of ones, it means if there is no variation in the regressor column, so the regressor column can exactly be written as some combination of the column consisting of ones. So there must be variation in, and जब हम आगे बढ़ेंगे we realize that beta or these coefficients or the sample value of these beta consist of a term in the denominator which is denoted by summation xi square, where xi is the small xi square. If there is no variation in xs, then there is no variation in mean as well, and that's why the summation goes to 0 and your beta is almost infinity. So assumption of full column rank for a two variable linear model with a constant term implies that there must be variation in the regressor x. And if it is a situation for your model, it definitely means that there is a flaw in the data set, because the possibility is there that you could have drawn a sample in which there was variation in x, but somehow you could not, due to whatever limitations that you had. Is that clear?
Yes sir, thank you sir.
Yeah. Okay.
So,
Haji.
if you are taking two variable case, then the maximum rank could be 2 now.
Come again?
If you are taking two variable case, the maximum rank should be 2 now only.
Yeah. Maximum rank has to be 2, because there are two columns, including the intercept term.
Okay.
Enough?
सर
Yeah.
इसको आइडेंटिफिकेशन कंडीशन क्यों बोलते हैं, फिर से बताएंगे?
Let us go ahead, because identification condition is related to the formula which is for beta. That is, beta को आप देखोगे तो x transpose x inverse का term contain करता है, और inverse of a matrix is not possible as long as the determinant of that matrix is 0. I'm sure that आपने पढ़ा होगा कि अगर rank, अगर कोई matrix 3 by 3 है, उसका rank अगर less than 3, it means determinant of highest order is 0. So inversion उसका possible नहीं है, इसलिए इसको identification condition बोलते हैं. I'll tell you about this, but just for the time being, just understand that this is called identification condition.
Yes, sir.
Okay, shall I move ahead?
Yes, sir.
Haji. Okay, let us come to assumption number 3. This assumption is called as assumption of regression. बहुत ही important assumption है, because this completely defines your model, and this also defines the way you want your error term to behave in the model. So what this assumption tells us is that the regression or the disturbance is assumed to have conditional expected value 0 at every observation. Now, what it means? What it says that the disturbances is assumed to have conditional expected value 0 at every observation. In symbol, this is written as, this is the expectation symbol if you are not familiar. Sorry. UI, conditional expectation. It means this is the disturbance term. This is conditioned on something. This is conditioned on what? This is conditioned on the data matrix that you have. The expected value of UI conditioned on X, that's why it is called as conditional expected value of the disturbances is 0. This also automatically implies that expected value of each of the disturbance term pertaining to the observation they all are equal to 0. Now, what it means is, what this assumption tells you is that the mean of or average of each of these residuals, residuals I should reserve for the population, sample, average value of each of these errors conditioned on all observations xi, which I've written as the matrix X, is 0. In other words, this conditional mean assumption, it states that no observations on X convey any information about the expected value of the disturbance term. So what our assumption at this point tells us is that there is no information about expected value of error term which is contained in any of the observation of X. That's why I have written this as well. That is, conditional expectation of the error term for first observation on the entire data matrix is 0. Conditional expectation of the second error term on the entire data matrix is 0, so on for the nth error term. Now, there is a very, very important point over here is that apart from no information.
Sir, doubt है.
Yeah.
ये जो आप x, this x is this for a particular x or is this for the whole of x?
Whole of x. That's why I've written
Okay.
in the capital letter X.
Yes, yes. Thank you, sir.
है ना? That's why I'm saying that conditional expectations or your average value of any of the error observation, be it first error, second error, say like nth error observation, information is not contained in any of the x's that you have in the model.
All right, all right. Yes, sir.
That's why it is condition on the entire data matrix. Is that clear?
Okay, sir. Yes, sir.
Okay. So this assumption is also called as exogeneity of the independent variables. So this exogeneity of the independent variables means that each of the disturbing terms is assumed to have zero expected value. In other words, this assumption also means that the disturbances are purely random draws from some population and that no observation on X convey any information about the expected value of the disturbance. In other words, mu and X are uncorrelated. Now if I just stop here by saying that mu and X are uncorrelated, the purpose does not stop here. What it also means is that not only mu and X are uncorrelated, error term and any function of the explanatory variables are also not related. That is, if you have written in the model, beta naught plus beta 1 x1 plus beta 2 x2 plus ui, what it means is this assumption that expected value of ui condition on x is equal to 0. What it means that not only mu I and x1 and x2 are not uncorrelated only, it also means that there should not be any correlation whatsoever of ui with xi square or xi cube or x1 x2 or log of x2 or any functional form of these variables. And this is a very, very strong assumption which has huge implications. And I'll discuss about this a lot more when we go ahead with the violation of these assumptions. But for the time being, just understand this, that this assumption of regression is also called as exogeneity of the independent variables, where exogeneity just tells you is that these disturbances are purely random draws from some population and that no observation on the data matrix, whether it is related to x1 or x2 or x1 square or any information about the expected value of the error term is not contained in the data matrix. So you maintain a full arm's length amongst the explanatory variables and the random error term in the model. So what this assumption automatically means here is कि अगर ये conditional mean error term का, that is, if ui condition on x is 0, it automatically means that unconditional mean has to be equal to 0. And this follows from law of iterated expectation. Sorry. What it says that if the conditional average value of ui on the data matrix is 0, then unconditional expectation of error term also automatically is 0. I ask you to prove it for me. Please do it yourself in the next class. If you find it, just tell me. Otherwise, I'll discuss this. This is based on an idea which is called law of iterated expectations. And just try proving yourself that agar conditional mean of error term on the data matrix is 0, it automatically implies that unconditional mean is also 0. Please solve this. And this is a very, very important assumption, because what it does is What it does is, if you actually follow, so how did I write my model? Now if I take conditional expectation both the sides on the data matrix, ये तो as it is आ जाएगा, because this is nothing but the data matrix itself, plus, and this by assumption is 0, it means that regression of y on x is nothing but the conditional mean of y given x. And that's why you should be able to understand now that when you interpret these coefficients, you interpret them in terms of average. That is, this beta tells me that if x changes by a very small amount, on an average, how y changes. And that on an average interpretation comes from this conditional expectation part. We must understand that without this assumption of conditional mean of error term going to 0, this x beta, which is also nothing but the linear combination of your x's, which is the conditional mean of y given x, it would not have been possible had this assumption been violated. So, assumption 1, that is your linearity, coupled with assumption 3, clearly defines your, or they comprise the linear regression model. The rest of the other assumptions are about how you specify the characteristics of error terms in the model. So again, I'll repeat, this assumption of conditional mean of error term on the data matrix getting to 0 means that there is not only or no correlation between u and x's, but mu, that is error term, is uncorrelated with any functions of these explanatory variables. And what it means is that no observation of the data matrix convey any information about the expected value of error term. And this assumption also helps us establish that regression of y on x is nothing but conditional mean of y, which is given by x times beta. That is nothing but linear combination of x's. Let us look at one more assumption, then I wind up the lecture. And that assumption is commonly referred to as assumption of homoscedasticity plus non-autocorrelation. And combinedly, this assumption is called as assumption of spherical disturbances. Now, what this assumption is all about? Again, I told you that this assumption is about the disturbances part, and it is combination of two main important concepts that are used in econometrics a lot, which is your homoscedasticity. Again, homo means equal and scedasticity refers to variance. So it talks about equal variance. अभी हमने देखा था expected value of ui going to 0 in the last assumption. Now we are talking about the variance of these error terms, variability of these error observations. And the non-auto correlation is auto means self and correlation means correlation with self. It means error terms are not correlated with each other. So basically this assumption of homoscedasticity and non-auto correlation, which is combinedly referred to as the assumption of spherical disturbances, these assumptions are exactly about variances and covariances of the error terms. Let me write it here. This assumption concerns about variances and covariances of these error terms. Whereas assumption of homoscedasticity, what it means that each of these error observations have equal variance. It means that variability of the error term is not a function or does not depend on the explanatory variables in the model. It means that variability of the error term does not change as x changes. बहुत ही common example find कर सकते हैं आप. If you're talking about profits of firms, so what this homoscedasticity assumption means that the variability in the profit earned by firms do not depend on the size of the firms. Similarly, if you're trying to talk about consumption and expenditure, what it says that variability in consumption expenditure does not depend on the income level of the consumers. In mathematical notation, I write this assumption of homoscedasticity as variability, variance of UI, and since we are talking about condition, so variance of UI condition on the data matrix X is sigma square, and there is no subscript attached to it here. That is, variance of U1 condition on X is sigma square, variance of U2 is sigma square, variance of U3 is sigma square. So like variance of UN, that is nth error term, still has equal variance. It means there is no variability in the error term. And this must be for all I starting from 1 till n. This assumption of constant or equal variance is called as homoscedasticity. And this assumption gets violated almost all the time when you're dealing with cross-sectional data. That is, you are having data on a single variable collected at a point in time across different sections of the population. And then the assumption of non-auto correlation means what? Auto stands for self and correlation means having that linear relationship. So what it says that covariance, because linear relationship is denoted by the term covariance. So covariance between UI and UJ conditioned on X must be 0 for all I not equal to J. Because if I is equal to J, then the covariance of X with X is nothing but variance of X. That's what this I not equal to J is all about. So this is your assumption of non-auto correlation. That is, you assume that your error terms are not correlated with each other. Previous error term has got no influence whatsoever on the current error term or on future error terms. This is what we mean by non-auto correlation. And this assumption gets violated most often in time series observations. Because ultimately time series observations are observations on a single recorded value across different time periods. So there's bound to be a case where previous period error term influences the current error term, and hence they are, or these error terms are auto-correlated. So in time series setting, the problem of autocorrelation comes, and in cross-sectional setting, the problem of heteroscedasticity comes. And mind you, these are the four main assumptions of CLRM. एक और assumption है जो कि generally assumption नहीं होता है, because the way OLS method proceeds, that automatically gets fulfilled. That's why I'm not counting that as an assumption, and that is called as, but बहुत सारे टेक्स्ट बुक में आपको लिखा हुआ दिखेगा, that is called as assumption of normality of error terms. Again, I repeat that this is not exactly an assumption which is required. It automatically gets fulfilled if you are solving the process through ordinary least square method. What it means, अभी हमने third assumption में क्या देखा, that expected value of UI is 0. Fourth assumption में हमने देखा that variance of UI condition on X is sigma square. And I'm sure that since these are stochastic elements, these must be these must be accompanied by a probability distribution. And since we're talking about distribution, the two main important parameters of a distribution is nothing but the measure of central tendency and measure of central dispersion, given by mean and variance respectively. So I know that these error terms, UI, they come from a population. I don't know what kind of distribution is that. They come from a population having zero mean and constant variance sigma square. And then we add to this that these error terms are normally distributed. Now, why are we assuming these error terms to be normally distributed? Because this assumption helps us in estimation. This assumption helps us in carrying out inference process based on these coefficient parameters. So this assumption of normality of error terms is not a required assumption as far as OLS is concerned, but this is very helpful when you go for the statistical inference when hypothesis testing is concerned. But understand that this assumption is just about, I told you that, apart from the assumption 1 and 3, which defines the form or functional form of the model, rest is all about how we want our error terms to behave in my model. How I want my error terms to behave? I want my error terms to behave and in such a manner that the conditional average of the error term is 0 for each observation. The variance of the error term, condition of the data matrix, must be a constant term. It means I'm assuming, or I want the error term to come from a population having zero mean and constant or equal variance, and then we add this extra requirement by saying that error terms are just not independently and identically distributed, they're also normally distributed. Whereby this distribution has mean 0 and variance sigma square, or given by a constant term. So we are done with assumptions of CLRM, and the reason I have covered it quick because I request you to go through Woolridge, whichever chapters are relevant as far as assumptions of CLRM is concerned. Once you are done with Woolridge, you want to study higher, then you must read William Green. I refer to that textbook as far as my lectures are concerned. And till up to hypothesis testing, at least we'll proceed with the matrix notation, and then we'll see if we can proceed with the violations of OLS in non-matrix fashion. But let's see how it progresses. So I urge you to read on Assumptions of Clrm from these textbooks. One is your Christopher Bullrich. Just look at the chapters which are relevant as far as Assumptions of Clrm is concerned. And if you're done with reading these basic lines or basic underlining about assumptions, I refer you to read William Green Econometric Analysis 5th edition or 4th edition, whichever edition you find. Almost they are same. Very few problems that are mentioned in the chapter.
सर आई हैव अ डाउट.
हाँ जी.
सर आपके YouTube वीडियोस में ये कवर्ड है क्या सर? आई वाज जस्ट आस्किंग.
Yeah. So again, as my last lecture, this is not a compulsion for anyone, but on my channel up till violations are covered. Violations of Clrm is covered. So this OLS assumptions and whatever lecture that we'll have later on, that is in our course, that is tomorrow, they all are covered on my channel. So अगर आप यहाँ पे मिस कर रहे हो, again advisable है, कोई compulsory नहीं है, क्योंकि बहुत सारे online resources available हैं. So you may go through that.
Sir.
हाँ जी. हाँ जी बोलो.
I have a doubt, not regarding this, but like the whole class has a doubt. We just got microeconomics periodical 2 and 3 marks. So in periodical 3 marks, there are many students, including me, who sat for the exam but are marked absent in the answer sheet. Like
I think during the lecture, I'm sure that you'd heard that Shrikant had called me. So I look after this. Don't worry. Actually, there is some bit of confusion who has given, because on the mail I see whosoever students have given, I have marked them. But then again, I got a call from Shrikant saying that there are students who are not marked. So I'll just look at it. Don't worry.
So we've also prepared a list in case you need it.
चलेगा, अगर आप मेल कर दोगे तो मुझे बहुत अच्छा लगेगा. Like it will be. I have so many papers to check that there's lots of confusion amongst the papers.
So we have made a list of people who've been marked absent, so I'll forward it to you.
चलेगा, हाँ, that will work. Yeah.
Okay, sir. Thank you.
Sir.
हाँ जी.
सर जो आपने अभी हमें क्वेश्चन दिया है ना प्रूव करने के लिए,
हाँ.
लाइक एक जनरल कंसर्न है, क्या उसमें सेंट्रल लिमिट थ्योरम हम यूज करेंगे उसको?
नहीं, जस्ट टाइप ऑन गूगल लॉ ऑफ इटरेटेड एक्सपेक्टेशन. देखो इटरेटेड एक्सपेक्टेशन क्या है डियर? इटरेटेड एक्सपेक्टेशन इज एन आइडिया कि which tells you that smaller information set dominates. Meaning what? कि मान लो एक कोई रैंडम वेक्टर है W या Z और उसका एक सब पार्ट है, let's say y is a sub part of the random vector W. That is, if you know W, you also know y. That's the main part of it. So if you take an expectation of y, or if you calculate average value of y or average value of W, the moment you have information on W, you also have all the information on y, which is what the law of iterated expectation is. कि अगर conditioned on something आपको पता है, तो जो larger information set होगा, that will automatically follow from that. Just try this. नहीं होगा, I'll solve that.
Sure, sir. Thank you, sir.
Hello, sir.
Adi.
Sir, what about the syllabus that we have left in macro and maths?
Naveen, let me find out time here. I'll definitely at least take macro classes, but let me talk to the coordinators on which days you guys are free.
Okay, sir.
सर एक ऐसा नॉर्मल सजेशन है, क्योंकि हमारा भी लाइक जो शेड्यूल है वो थोड़ा हेक्टिक है, लाइक सैटरडे को भी क्लासेस, संडे को भी क्लासेस. सो लाइक मुझे ऐसा लग रहा है कि अगर आप मैथ्स का क्लासेस अगर रिकॉर्ड करके लाइक आपके जैसा फ्री टाइम है अपने अकॉर्डिंग और जस्ट अपलोड कर दोगे तो लाइक हम भी फ्री होंगे उसको जस्ट कवर करने के लिए. because it's a part of basically learning. हम एग्जाम के लिए तो पढ़ नहीं रहे, तो ऐसा.
ठीक है. I think I'll see to that moment. Thank you so much. I'll definitely look into this aspect.
Sure, sir.
Okay. Any doubt related to today's lecture? I want those doubts also. किसी को doubt है आज के assumptions?
Sir, I have a doubt.
हाँ जी.
Sir, I joined a bit late, but I had a doubt. Sir, derivations आना compulsory है क्या sir? The concepts.
अभी हमने derivation किया ही नहीं में. Why are these talks coming?
Okay, sir.
Any doubts as far as today's lecture is concerned? Yeah, Himani, go on.
Could you please repeat the additions ones of the books?
Come again. Could you please say a bit louder?
Additions of
Additional book. Additional book is there. William Green, Econometric Analysis. William Green, Green.
Which edition is it?
Third, fourth, fifth. Latest is 5th edition. But if you get any edition, that would work.
Thank you, sir.
Yeah.
Sir, in the assumptions of multicollinearity, you said there shouldn't be an exact multicollinearity between the explanatory variables. If the explanatory variables itself are in a form of regression function, then it is up to the researcher that how much degree of correlation is allowed, or there is a certain cutoff.
Correct.
Is there a certain cutoff, sir, or
there is no cutoff there? It all depends. See, पूरा econometrics trial and error पे है भाई. कि आपको हमेशा देखते रहना होता है कि चलो ये मॉडल फिट नहीं हो रहा है, इसमें अगर ये थोड़ा इम्प्रूव करेंगे तो there is no cutoff as such. There are though techniques which are there, but again they are not hard and fast techniques. Like there are techniques you look at, the adjusted R square or then variance inflation factors are there. They are just indicative, but there is no cutoff as such. कि हाँ इस इतने multicollinearity पे मैं रुक जाऊंगा. It's purely a trial and error.
Okay, sir. Also, because if some of these assumptions are not followed by the regression or the function, then there are ways to correct these, right?
Yeah.
Will we be doing that?
That's what we'll do when violations of these assumptions are there. Okay. Heteroscedasticity होगा तो क्या होगा?
Yes.
Auto correlation होगा तो क्या होगा? Functional form गलत है तो क्या होगा? वो सारी चीजें हैं.
Okay.
Sir.
And sir.
हाँ जी.
Himani.
Chapters भी होते हैं ना फिर.
Yeah, you have to read that. What is there to read on all these chapters?
Because उसमें बहुत सारे फिर टेस्ट भी होते हैं उनको प्रूव करने के लिए, further और assumptions उनमें.
Assumptions के लिए टेस्ट होते हैं प्रूफ करने के.
जैसे हमने पार्क्स टेस्ट, ग्लेजर्स टेस्ट ये सब पढ़ा था.
They are remedial measures there. They'll come when we discuss violation of these assumptions.
अच्छा, okay sir.
Sir.
They are remedial measures when you have such violation of assumptions are there. I'm just asking you to read these assumptions.
Sir.
हाँ जी.
सर एक रिक्वेस्ट है एक्चुअली, लाइक पर्टिकुलर अगर हम इकोनॉमेट्रिक्स की बात करते हैं तो उसमें डेटा का रोल बहुत इंपॉर्टेंट होता है. लाइक सैंपल बेसिकली कितना लार्ज होगा, कितना स्मॉल होगा. सो एक रिक्वेस्ट है कि इन प्रैक्टिकल सेंस व्हेन वी आर डूइंग द रिसर्च एंड ऑल, सो वी नीड द सैम्पलिंग मेथड, लाइक कितना एग्जैक्ट नंबर लें. तो सर इसके बारे में भी आप लाइक फर्दर आप बताओगे?
या ठीक है. या आई शुड इन फैक्ट.
ओके, थैंक यू सर.
Sir.
हाँ जी.
So there is a sort of a cutoff fix, like when we use T distribution and Z distribution के लिए, that the sample should be greater than or less than 30. I want to know how is this 30 being specified?
You see, Ayushi, there is no such rule as such. These are the rules that we have ourselves made. And why exactly? Because you see, it completely depends on the research in question. And why I'm saying that, अगर आपने पढ़ा होगा, let us start from the basic part. You have read these class interval, class size, frequency, right?
Yes, sir.
है ना, क्लास इंटरवल का साइज आप मैक्सिमम 5-10 रखते हो. सो आइडियली जब ये पहले सारा चीज तो मैनुअली होती थी, तो क्या इन्होंने नोटिस किया कि जब क्लास साइज बहुत ज्यादा बढ़ जाता है या नंबर ऑफ ऑब्जर्वेशंस आर वेरी लार्ज, देन making an appropriate class interval of more than 30 is really cumbersome or is really tough. तो हमने अपनी सुविधा के लिए हमने अपने कंफर्ट के अकॉर्डिंग क्या बोल दिया कि जो 30 नंबर ऑफ ऑब्जर्वेशन से ज्यादा होगा, since it is difficult for us to to have more than 30 class intervals, so we say that if you have data size which is more than 30 observations in total, that comes as large sample, which is absolutely, as a researcher, you should never think like this. It definitely depends on problem at hand. So suppose I want to find out कि इस एरिया में, suppose किसी को पता चला कि गोखले के नीचे, लैंड के नीचे गोल्ड छुपा हुआ है. If I go by the idea कि मुझे 30 जगह पे पहले तो डिग करके देखना ही होगा, क्योंकि 30 is a large sample and 30 के नीचे 30 के ऊपर मैं Z टेस्ट लगा नहीं पाऊंगा. I'll be absolutely a fool. In that case, I'll end up digging entire Google. So the idea here is that we definitely say that if your N is greater than 30, you should employ Z test. But again, I'll say कि as a researcher mind, you should always look at कि आप किस variable पे और किस problem से deal कर रहे हो. So there is no hard and fast rule as far as these samples are concerned.
So, but then, yes, sir. So, but then, why is this sort of assumption still in place when we, like, all of the research is not just on 30. Like, most of them are greater than, the sample is greater than 30.
You're not getting the point. ये 30 जो cutoff decide हुआ था, 30 was based on the class intervals. Because drawing a histogram or drawing a frequency distribution chart for more than 30 class interval is really tough. Because you see, class intervals जब बहुत ज़्यादा हो जाते हैं, class size और number of observations जब बहुत huge हो जाता है, तो वही discrete observation आपका continuous observation में convert हो जाता है. तो just एक n greater than 30, n where refers to as की number of observations or sample size. But again, अब जैसे मान लो suppose मुझे income of residents of Pune निकालना है, तो क्या if I just take 31 observation, can I generalize for the entire population of Pune? Will I do justice to that? No. Do you understand what I'm saying? तो वो एक completely dependent है कि आप कौन सा problem और किस variable की बात कर रहे हो. अगर उसमें मान लीजिए observation की संख्या बहुत ज्यादा है, तो just having a sample size greater than 30 does not solve any purpose.
Yes, sir. Got it, sir. Thank you, sir.
Okay.
Sir, the practical aspect Mohit is talking about, can we do it along the classes rather than just doing it in the end? ताकि हमें कोई रिसर्च या कोई प्रोजेक्ट करना हो तो हम अपनी अंडरस्टैंडिंग के साथ उसे कर पाए अभी.
या हिमानी, बट अभी एटलीस्ट assumption में कोई empirical part नहीं है ना dear. Assumption में derivation. Once we proceed ahead, once we proceed ahead, we'll do at least 2-3 computer exercises from Woolwich, so that you are in that habit of solving these problems on software. Excel में करो, R में करो, जहाँ भी तुम्हें पसंद.
Okay, sir. Thank you.
ठीक है.
हेलो सर, मेरा आज पहला लेक्चर था. इससे पहले कितने लेक्चर हुए और उसमें क्या पार्ट कवर किया है, इसके बारे में कुछ बता सकते हैं?
या प्लीज टॉक टू द CR और कोऑर्डिनेटर्स.
ओके,
या
थैंक यू सर.
सर,
हाँ जी.
Sir, in the second assumption of full column rank, you talked about a two variable model in which the intercept, that beta naught, the vector with all ones, was supposed to be, if that is there, then all the x is the data vector should have certain variation.
Correct.
So if this is for the two variable, if there are three variables, what does the intercept relation, the intercept being there signify?
Come again? I didn't understand what you're asking.
I mean, if there is the intercept term and one variable, then you said there should be enough variation in the data, the regressor value, so that there's no linear relation between the intercept vector and the data vector.
Mm-hmm.
Right. So if there are three variables, that means x1 and x2.
Yeah.
And the intercept, then is it supposed to be that x1 and x2 should not be correlated, and even the intercept vector should not be correlated? All of them should not be correlated by any chance.
They should not be perfectly collinear. There will always be degree of correlation amongst the variables.
Okay.
It should be like कि ऐसा नहीं होना चाहिए कि एक कोई जो एक्सपेरिमेंटिव वेरिएबल है वो परफेक्टली एक मल्टीपल है दूसरे एक्सपेरिमेंटिव वेरिएबल का. समझ में आई बात?
ओके सर. यस.
सो इस पर्टिकुलर अजम्पशन में अगर सिंगल वेरिएबल है, मींस सिंगल एक्स है एंड अदर वन इज बीटा नॉट, तब हम ये कह रहे हैं इसका इम्प्लीकेशन यहाँ पे है कि काइंड ऑफ देयर इज अ वेरिएंस, लाइक वेरिएंस जो एक्स में कितना है, एंड अगर मतलब नहीं है तो इट्स अ फ्लॉ, एंड इफ देयर इज मोर देन वन, लाइक x1 है, x2 है, x3 है, तो हम कह रहे हैं कि उनका x2 और x3 जो वेरिएबल्स है उनका लीनियर इंडिपेंडेंस चेक कर रहे हैं, राइट सर?
करेक्ट.
तो सर ये दोनों इंटरप्रिटेशन क्यों चेंज हो जा रहा है ऐसा?
क्योंकि जब एक ही वेरिएबल है तुम्हारा, एक वेरिएबल मींस कि यू जस्ट हैव टू कॉलम्स, उसमें एक कॉलम सिर्फ 1 का है, तो वेरिएशन होने का मतलब क्या है कि जो सेकंड कॉलम है तुम्हारा, वो सेकंड कॉलम ऐसा नहीं होना चाहिए कि उसमें कोई वेरिएबिलिटी नहीं है और वो एग्जैक्ट मल्टीपल हो जाए कॉलम 1 का. That's why this interpretation is there. And this is just one corollary कि आपका सिंपल 2 वेरिएबल मॉडल है जहां पे सिर्फ सिंगल एक्सपेरिमेंटिव वेरिएबल की बात चल रही है, वहां पे इसका इंटरप्रिटेशन ये है कि आपका जो रिग्रेसर है उसमें एक वेरिएबिलिटी होनी चाहिए. अदरवाइज वेरिएबिलिटी मींस व्हाट? वेरिएबिलिटी मींस कि जो आपका एक्सेस है, जो आप ऑब्जर्वेशन कलेक्ट कर रहे हो 100, 200, 400 जितना भी ऑब्जर्वेशन है उसका, उसमें आपका देयर इज सम डिग्री ऑफ वेरिएंस. That is, not all the observations are same. That's what variability means.
Okay, got it, sir. Thank you.
हाँ जी. Any other doubt?
सर जब हम मॉडल बनाते हैं,
हाँ जी.
तो उसमें लेट्स से इफ वी आर स्टडीइंग अबाउट मेल्स एंड फीमेल्स, तो उसमें बेटर होता है कि हम डमी वेरिएबल इंट्रोड्यूस कर दें या फिर उसको x1 x2 की तरह कंसीडर कर लें?
When you see dummy variable हम कब यूज करते हैं? And why do we use dummy variable?
क्वालिटेटिव के लिए जब कैटेगोरिकल भी होता है.
So अगर आपका मान लीजिए कोई वेरिएबल है जो कि क्वालिटेटिव इन कैरेक्टर है, क्वालिटेटिव इन कैरेक्टर मींस, एंड व्हाई वी यूज डमी वेरिएबल? बिकॉज उस क्वालिटेटिव वेरिएबल को मैं क्वांटिटेटिव में बनाना चाहता हूं. जेंडर, रेस, सेक्स, रीजन, रिलीजन, दे ऑल आर क्वालिटेटिव वेरिएबल, बट हाउ डू आई count them? Statistics is an idea which converts or which only works when you have quantitative character variable. पर जहां पे क्वालिटेटिव वेरिएबल आएगा उसको मैं काउंट कैसे करूं, उसको मैं नंबर कैसे प्रोवाइड करूं? That's why dummy variables are used. Otherwise, concept remains same.
Okay, sir, got it.
So, जैसे मान लो तुम वेज और फीमेल एंड मेल का देख रही हो, तुम्हारे पास मान लो 100 ऑब्जर्वेशन है, उसमें 60 फीमेल है, 40 मेल है, ये तुम्हें कैसे पता चलेगा अनलेस तुम काउंट करो सबको? तो व्हाट यू डू इज यू हैव अ कोड कि भाई जो भी ऑब्जर्वेशन है वो मेल होगा, उसको आई गिव 1, फीमेल होगा आई गिव 0, एंड देन यू काउंट ऑल द नंबर ऑफ वंस एंड ऑल द नंबर ऑफ 0. That gives you the count of number of males and number of females, which becomes a quantitative variable now. Not right, but
Yes, sir.
so what instead you are doing is you are converting a quality or attribute variable into a quantitative variable so that you can apply statistical techniques to them. You cannot apply statistical techniques to a qualitative variable which cannot be counted. ठीक है?
Yes.
We deal with all this. Dummy build अभी हमने just start किया है, इतना आगे अभी नहीं बढ़ते हैं. ठीक है?
Yes, sir.
Okay then.
Thank you, sir.
Tomorrow. And
Thank you, sir.
safe. Yeah.
Thank you, sir.
Yeah.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.